Good morning. So we will start today a new analytic task. Before mid-semester, we learned one analytic task and another task which is closely related to that. So what we learned was we learned classification and we learned the prediction, which is very closely associated with classification. Okay, so these are the analytic tasks that we had learned. So now we will learn a new task which is called as association. So today we will start learning about association, and let's first understand what are the basic concepts associated with the association. Then we will look at some ways in which we can carry out the task given a data set. So let's understand first some basics with the association. It is a strength of co-occurrence between one item or the other. So the item may give you some perspective. You may, if you want to generalize it, you may say one thing to another thing. But then the idea is that here, okay, if you look at it very simply, many times the association classic problem is the market basket analysis. So in market basket analysis, the interesting ideas or the findings that we expect is that when the people who buy potatoes, do they also buy onions? So, and the people who buy bread, do they also buy butter? So these are the associations that we want to see. Of course, our intention is not to do a root cause analysis and find out why is it that these people are finding this with this. That may be done separately by some domain expert to understand what makes somebody pick some item along with that. But uh, at the data analysis or data science level, we'll stop at understanding the analysis given a big data set. So we will possibly, we want to first find out the co-occurrence, strength of co-occurrence. We need to have a measurement for the co-occurrence to say that, okay, there seems to be a stronger association between these two than two others. While the classic concept problem is the market basket, but there can be many other problems which can be defined as a problem of association. So, for example, if you want to find out uh, the the school children who have interest in, let's say, a particular game, let's say they are interested in, let's say they are interested in reading the books. Do they have interest in the playing video games? Is there a strong co-occurrence between the two? The students who participate in sports, do they end up getting doing well in literature? So is there a co-occurrence? Or the people who are having this particular type of personality, will they be resistant to the drug? So the idea is that the while the problem is all about market basket, we'll start and we will, that's where we spend the time. But you can generalize association to solve many types of problems. So we will simply take this as one of the analytic problems, and we will take market basket as an example to understand how to solve the problem. So looking at it from the machine learning perspective, this is representing unsupervised machine learning. Okay, this is unlike classification. This is unsupervised. this is to say when a data set is given to the machine and asked to learn the associations within the data set, there is really no reference or training data set which is used by the machine to learn how to find the association and accordingly find the association. So it's a unsupervised learning, and once the associations are found, we can convert them into rules. They are used in a wide range of applications. So here are some examples, and then this is just a explanation from one domain perspective. What can a grocery store or a retail store do if they understand the association? So probably they can think in terms of a bundle price, saying that if you buy these two together, there is something, and it is possible that they may decide to keep those products together in a store, or they may be able to try out several ideas once they recognize the co-occurrence or the strength of co-occurrence. So let's look at a set of market transactions. So this is to say one customer goes, picks up bread and milk and checks out. So pays for the bread and milk and goes. Then another customer goes to the store, picks up bread, diaper, butter, beans, and then his basket is checked out. So now these are the 5 transactions. So we have taken very simple data set in order to do the calculations easily in the class. So now having got these 5 transactions, we will start looking at the associations. So the association rule can take this type of form, saying that the people who buy diaper tend to buy butter, or the people who buy butter and bread also tend to buy milk. So these are the examples of association rules, which we will be able to draw once we understand the co-occurrence patterns within this data. So as we have discussed, the co-occurrence is only co-occurrence. We have no intention to do the research in causality, so that we will leave it to some other experts. So now we will come to defining some nomenclature or terms, and that will enable the discussion on association mining. So first we will decide that each transaction or each basket consists of set of items, and when we take items in a group, so here there is a bread, diaper, butter, beans. Let's say we are referring to beans and bread. When we are referring to these 2 items together, we will call that as an item set. So that can be any number of items, but a unique set of items. Then once this is the item set, and we will also use the nomenclature k item set to refer to an item set that has 2 items, k items. So in this case, this is what? This is 2 item set. And what about this? This is 3 item set. Okay. Now, next thing is that we want to find the support count, which is sometimes represented as sigma. So The support count is representing the frequency of occurrence of an item set. Let's take the item set, this three item set, milk, bread, diaper. We check how many times it is occurring. Milk, bread, diaper, it is occurring in the third transaction. Is it? No, sorry, fourth transaction. Milk, bread, and diaper. It is also occurring in the fifth transaction. So it is occurring twice. So we say that the support count for the item set milk, bread, diaper is 2. The same thing can also be represented sometime as a fraction, sometime it is represented as a percentage. So when we represent this as a fraction, we say 2 out of the 5 transactions. So that is 2 by 5. So this 2 by 5 can also be represented as 0.4 or 40%. So the support can be expressed in numerous form: absolute count, fractional count, then percentage. And we generally define in this problem a threshold. And what we do is that if the threshold is exceeded, then we refer to the item set as a frequent item set. So now let us say we put 30% as a threshold. Then milk, bread, and diaper is becoming a frequent item set because it has a 40% support count. So the support percentage is coming to 40%. But then somebody thinks that the support threshold should be 60%. Then this is not going to be frequent. So now let's look at association rules. So it's something of the form X implies Y, where X is an item set and Y is an item set. Then we refer to this as an association. So we can take an example: milk and diaper imply butter. So in a way we are saying that if a person buys milk and diaper, person is also likely to buy butter. So again, that we need to express based on the data sets study in some metrics so that we can express the goodness of this rule. So the way we will evaluate a rule is using two measures. One is support and the other is confidence. So support, as we defined it, represents the fraction of transactions that contain both X and Y. When we are talking about association rule, the support for X implies Y is analyzed by taking the support for X union Y. So in this case, milk, diaper, butter together they have to occur. Their support, as we have seen, is 40% or 0.4. Then we use another measure for the evaluating the rule, which is the confidence. Confidence measures how often items in Y appear in a transaction which already contains X. So this is, we may write this as a conditional probability. Probability of Y given X. So this will be written as probability of X union Y divided by the probability of X. So now if we look at milk, diaper, butter, it is occurring in 2 transactions. Milk and diaper are occurring in 3 transactions, 3, 4, 5. So confidence is 2 by 3, it is 0.67, sometimes it is written as 67%. So now given set of transactions, the association rule mining, what does it do? It finds the rules that have a support greater than minimum support threshold and the confidence that is greater than minimum confidence threshold. So that will help us find the interesting association rules. because some domain expert decided that for this domain the confidence level of 60% is great and support of some 30% is great and so on. Then we are going to use those counts and find out all the associations. So how do we get those association rules? One approach, which obviously we will not do because we are calling it brute force approach. We will look for really smarter approaches which can be optimal and efficient with respect to resource usage and fast and all that. So, but then a simplest brute force approach is to list all possible transaction rules, compute the support and confidence for each rule, and prune the rules that fail the minimum support and minimum confidence threshold. And this is going to be computationally prohibited. So this is, but then this is a maybe this can serve as a reference to when we think of a better algorithm, we can see how much benefits we are getting with respect to brute force when we use an algorithm. So this is a simplest approach that we can think of. Now let's enumerate, given that we have a very small database, so we will be able to enumerate some rules and compute the support and confidence. So let's see, let's look at the milk diaper implies bread. Sorry, milk diaper implies butter. So now milk diaper butter. So this is transaction 4. This has milk diaper butter. So milk diaper butter is there in transaction 3. So now the support for milk diaper butter, all of them each 0.4 or 40%, 2 out of the 5. Now once we look at milk diaper butter, interesting thing is that we can formulate several rules, not one rule. So we need to find out which is the best rule. So we can compute the support and confidence. What we are doing is still we are working with the brute force approach, and we can see that all of these rules are representing the binary partitions from a single item set, milk diaper butter. Okay, and so because they represent coming from the same item set where we are making multiple partitions, so the support is same for all of them, but the confidence is different based on the way we are creating the partitions. So in this case, the confidence is 1 because milk and butter are occurring only twice together in the whole database. So when you calculate the confidence, the numerator and denominator both are 2 out of 5. So that is going to come as 1, or so it is 100%. So that means among these rules, you can have the maximum confidence with the rule milk and butter imply diaper. So now this is a very generic idea that if the rules are originating from the same item set, so they're simply the various binary partitions of the same item set. So they're going to have a same support, but then there is a different confidence. So in such cases, so our goal is to look for maximizing the confidence because the support for all these rules are same. So to find the association rules, So we are doing two steps. Step one, we are finding out frequent item sets. So that is item sets with high support. So here our focus is entirely support, where our intention is to do frequent item set generation, sometimes referred as frequent item set mining. So finding out, given a data set, find all the frequent item sets. So there our focus is entirely on the support evaluation. Then we generate the rules with the high confidence from the frequent item set. So from each frequent item set, we do the binary partition and we look at various binary partitions, and we want to generate the rule which is offering us a high confidence. So now if we look at these two steps, they look pretty good. But we need to find efficient ways for doing it. First thing is we need to find out frequent item set generation. If we have to do it through brute force, that is going to be very expensive. So we need to find alternative for that. So let's look at the possible frequent item sets, because because our intention, if it is simply to use a very simple approach, which is a brute force approach, then we need to see how many item sets will come out. So the number of item sets that come out, suppose that the store sells 5 items. Okay, so we are starting to use all the transactions in the data set, and we are generating the possible candidate item sets. So how many possible item sets will be there? Null, let's say null is one item set, which is no item set. Then A, B, C, D, E, these are the 5 items. So each one of them can be an item set. This will be a one item set. Then from these, we can generate 10 2-item sets. And then we can generate 10 3-item sets. And then we can generate 5 4-item sets. And we can have one 5-item set. So in general, this is going to be 2 to the power of d possible candidates, given that the store sells d items. Then we will have 2 to the power of d possible candidates. Now, if a store sells 1,000 items, what will be the number of candidates? Is 2 to the power of 1,000. If you remove the null, in this case, it is actually 2 minus 1, but we ignore that. This is a very small consolation compared to the big number of items candidates we are getting. So 2 to the power of 1,000 is going to be very, very computationally inefficient. So even for a supercomputer, this can take very long time to do the support, evaluate the support for each of the candidates. So the number of candidates is so large that it's going to be very slow. So we need to find a mechanism to reduce the number of candidates that for which we need to evaluate the support. So let's look at the challenges with the frequent item set generation, particularly when we use the brute force approach. So if there are W items that are sold by the store and there are N transactions and you need to consider M candidates, so then the complexity, essentially we are looking at how many times we need to calculate the support. So that is support is, how do you find the support for let's say there are 5 items in a transaction and you want to find out whether the transaction, 5 items in the frequent item set, and we need to find out whether the transaction does the support for that item set. So you need to compare each item in the transaction with each item in the item set. So if there are W items, so we need to take W times we need to make the comparison at least. So what it means that we need to do n times m times w times number of comparisons or the computing operations. So we can say that the complexity is of the order of n multiplied by m multiplied by w, where m itself is 2 to the power of d. If w is representing the same as the number of items sold by store, so then w itself will also be very big. But the so what we are saying is that this is offering us a huge computational challenge. So what can we do? We can reduce the number of candidates. We can reduce the number of transactions. We can reduce the number of comparisons. So there are techniques to reduce each one of them, and they all come with a price. But we need to try some of them to improve the efficiency of frequent item set generation. So we will look for a specific algorithm, which is the a priori algorithm. So a priori algorithm uses the specific a priori principle, which is saying that if an item set is frequent, then all the subsets are also frequent. It's pretty common sense, right? So if milk, bread, and butter are frequently bought, so obviously milk and bread are also frequently bought. Similarly, we can use the conversely saying that if X is subset of Y, support for X is greater than support for Y, what it means that if X is not frequent, Y can never be frequent. So that is the simple a priori property. Using that, we can significantly reduce the number of candidates for which we need to evaluate this. So this is referred as anti-monotone property. So if we take arbitrarily an example, let's say people seldom buy a lettuce. So let's say it is infrequently bought item in a grocery store. So lettuce, comma milk, you take two item set, lettuce and milk. So how frequently it will be bought? It will be very infrequent because lettuce is never bought frequently. It is bought by only one customer in a day. So obviously, if you take lettuce and milk, it can be at most one. It will be less than one. So that means if lettuce is infrequent, any subset, any item set that contains lettuce will also be infrequent. So that is the concept, and we will study the. We will take a break for a couple of minutes and